Tonight, we are going to explore one of the most extraordinary and perplexing discoveries in modern astronomy, a finding that has sent shockwaves through the scientific community and forced cosmologists to question assumptions they had held for decades. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has found something at the edge of observable reality that should not exist. Not metaphorically, not in the sense of being unexpected or unusual, but literally, physically, mathematically impossible according to our best understanding of how the universe works and how galaxies form. When astronomers first began analyzing the deepest images from Webb, images showing galaxies so distant that we see them as they were mere hundreds of millions of years after the Big Bang, they found galaxies that are too massive, too mature, too well-developed to have formed in the time available. These are not small discrepancies or minor puzzles that can be explained away with better measurements. These are galaxies that appear to weigh hundreds of millions of times the mass of our Sun, containing populations of stars that look evolved and chemically enriched, all existing at a time when the universe was barely 2% of its current age. The numbers simply do not add up, and if these observations are correct, then something fundamental about our understanding of cosmology must be wrong. Before we continue into this extraordinary story, if you enjoy these deep explorations into the frontiers of astrophysics and cosmology, a quick like or subscribe would mean a great deal. It helps support the channel and allows me to continue creating content that examines the biggest mysteries in science. Now, let us begin by understanding what the James Webb Space Telescope actually found and why it challenges everything we thought we knew about the early universe. The observable universe has an edge, not a physical edge where space ends, but an observational horizon beyond which we cannot see because light from those regions has not yet had time to reach us. The universe is approximately 13.8 billion years old, born in the Big Bang, and expanding ever since. When we look at very distant objects, we are quite literally looking back in time because of the finite speed of light. Light from a galaxy 1 billion light-years away shows us that galaxy as it was 1 billion years ago. Light from a galaxy 10 billion light-years away shows us cosmic history from 10 billion years ago. The most distant objects we can observe, the ones at the edge of observable reality, show us the universe as it was in its earliest epochs, just a few hundred million years after its birth. This is the realm that the James Webb Space Telescope was designed to explore, the cosmic dawn when the first stars ignited and the first galaxies assembled from primordial gas clouds. Astronomers had detailed predictions about what this early universe should look like. Computer simulations based on our best physical theories, fed with data from the cosmic microwave background and observations of the nearby universe, painted a clear picture. The first galaxies should be small, faint, and relatively simple structures, containing perhaps a few tens or hundreds of millions of stars, with low metallicity, meaning few elements heavier than hydrogen and helium, because there had not been enough time for generations of stars to synthesize and distribute these elements. These baby galaxies should be the cosmic equivalent of toddlers, small and undeveloped compared to the massive spiral and elliptical galaxies we see in the modern universe. But that is not what Webb found. Instead, when astronomers turned the telescope toward the deepest regions of space, targeting areas where they expected to find these faint infant galaxies, they discovered objects that looked shockingly mature and massive for their age. The most extreme example, a galaxy designated JADES GS-Z14-0, became the most distant galaxy ever confirmed, with a spectroscopically measured redshift of 14.32. This redshift corresponds to a time just 290 million years after the Big Bang, when the universe was barely 2% of its current age. At that early epoch, based on all our theoretical models and computer simulations, galaxies should still be in their most primitive stages, small clumps of gas and stars slowly coalescing under gravity. Yet JADES GS-Z14-0 spans over 1,600 light-years across and contains several hundred million times the mass of the Sun in stars. Even more puzzling, spectroscopic analysis revealed strong emission lines from ionized oxygen and hydrogen, indicating that this galaxy already contains chemically enriched material. Oxygen is not created in the Big Bang. It can only be forged in the cores of massive stars, and then scattered into space when those stars explode as supernovae. The presence of significant oxygen just 290 million years after the Big Bang suggests that multiple generations of massive stars had already been born, lived out their brief lives, and died, scattering their ashes across the galaxy to enrich subsequent generations of stars. This cycle of stellar birth and death normally takes many hundreds of millions of years to produce observable quantities of elements like oxygen. Yet here it was, already present in abundance when the universe was supposedly still in its infancy. Kevin Heinlein, an associate research professor at the Steward Observatory at the University of Arizona, and a member of the team that discovered JADES GS-Z14-0, described his reaction to the findings. He had spent months analyzing images from Webb's near-infrared camera, looking for candidate galaxies that might be at extreme distances. When JADES GS-Z14-0 first appeared in the data as a small red smudge, the team was initially skeptical. The galaxy appeared too bright to be at such an extreme distance. There were multiple ways that nearby galaxies with unusual properties could mimic the signatures of very distant objects. But follow-up observations using Webb's near-infrared spectrograph, conducted over nearly 10 hours of telescope time in January 2024, confirmed beyond doubt that this was indeed a record-breaking galaxy. The spectrum showed an unambiguous Lyman break, the sharp cutoff in emission at wavelengths shorter than 121.6 nanometers in the galaxy's rest frame, which appears shifted to much longer wavelengths because of cosmic expansion. This Lyman break is produced by neutral hydrogen gas absorbing ultraviolet light, and its presence at the observed wavelength left no room for doubt about the galaxy's distance. Heinlein described the moment they processed the spectrum as one of the great moments of his scientific career, made even more poignant by remembering the dedication of everyone who had worked to make the Webb telescope possible, including the skeleton crew that had stayed behind to protect the telescope during Hurricane Harvey years earlier, when the observatory was still being built. The discovery of JADES GS-Z14-0 was remarkable enough on its own, but it was far from an isolated case. As Webb's observations continued, and as astronomers analyzed more data from the telescope's deep surveys, they began finding numerous other early galaxies that appeared similarly problematic. The JWST, Advanced Deep Extragalactic Survey, or JADES, which discovered JADES GS-Z14-0, also found its sibling galaxy JADES GS-Z14-1 at nearly the same distance. Other surveys using Webb found additional examples of bright, apparently massive galaxies in the first few hundred million years after the Big Bang. When researchers conducted statistical analyses to determine how common these bright early galaxies were, they found that the number density, meaning how many such galaxies exist per unit volume of space, was roughly 10 times higher than pre-Webb observations and theoretical models had predicted. This was not a case of finding one or two exceptional outliers. Webb was revealing a population of early galaxies that seemed fundamentally different from what theory had expected. Some researchers began using dramatic language to describe the situation. Headlines spoke of cosmology being broken or of the Big Bang theory being called into question. A few astronomers even suggested that the age of the universe might need to be revised, perhaps doubled, to allow enough time for these galaxies to form. The standard model of cosmology, called lambda cold dark matter, or lambda CDM for short, had been extraordinarily successful for decades at explaining observations ranging from the cosmic microwave background radiation to the large-scale structure of galaxy clusters. But now, for the first time, it appeared to face a genuine crisis. To understand why these early galaxies are so problematic, we need to understand how galaxies are supposed to form according to standard theory. In the immediate aftermath of the Big Bang, the universe was extraordinarily hot and dense, filled with a nearly uniform plasma of elementary particles and radiation. But this uniformity was not perfect. Quantum fluctuations during the inflationary epoch, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang, seeded tiny density variations in the primordial plasma, variations of about 1 part in 100,000. These minute overdensities, imprinted in the cosmic microwave background radiation that we observe today, would become the seeds for all future cosmic structure. As the universe expanded and cooled, gravity began amplifying these initial density fluctuations. Regions that were slightly denser than average would pull in more matter from their surroundings, becoming progressively denser still. The process is called gravitational instability, and it operates on all scales from individual stars to galaxy superclusters. But in the early universe, most of the matter was in the form of dark matter, a mysterious non-luminous substance that interacts only gravitationally and makes up about 85% of the total matter content of the universe. Dark matter, being immune to the radiation pressure and other electromagnetic forces that affected normal matter in the hot early universe, could begin collapsing under gravity earlier than ordinary matter. These collapsing regions of dark matter formed halos, gravitational potential wells into which normal matter, primarily hydrogen and helium gas, would subsequently fall. Inside these dark matter halos, the infalling gas would shock and heat up, reaching temperatures of millions of degrees. Over time, this gas would cool through various mechanisms, radiating away energy and condensing toward the center of the halo. As the gas density increased, regions would eventually reach densities and temperatures high enough to trigger nuclear fusion, and stars would ignite. The first stars, called population III stars, were thought to be very different from modern stars. With no heavy elements available, since those elements had not yet been synthesized, these primordial stars could grow to enormous masses, perhaps hundreds of times the mass of our Sun. Such massive stars would burn ferociously hot and die quickly, exploding as supernovae within just a few million years of their birth. These explosions would seed the surrounding gas with the first heavy elements, carbon, oxygen, iron, and others, enabling subsequent generations of stars to be more like the stars we observe today. This entire process, from initial dark matter halo formation to the ignition of the first stars to the buildup of stellar populations massive enough to be detected as bright galaxies, was expected to take several 100 million years at minimum. Computer simulations based on lambda-CDM cosmology and detailed astrophysics showed that while some small galaxies might exist 200 to 300 million years after the Big Bang, they should be relatively rare and faint. Galaxies with masses of several hundred million solar masses should not appear until 500 million years or later. The brightest, most massive galaxies, comparable to what we see locally, should take billions of years to assemble. Yet here was JADES GS Z14-0, massive and bright and chemically enriched at just 290 million years, along with numerous other examples that seemed equally impossible according to these well-established theoretical frameworks. The galaxy JADES GS Z14-0 presents multiple challenges simultaneously. First, its sheer luminosity, meaning the total amount of light it emits, implies that it contains several 100 million solar masses worth of stars. For this much stellar mass to have assembled so quickly requires extraordinarily efficient star formation. The gas falling into the galaxy's dark matter halo would need to convert into stars at close to the maximum theoretically possible rate, with minimal losses to feedback processes. Feedback refers to various mechanisms by which forming stars and supernovae can heat or blow away the surrounding gas, regulating or even shutting down star formation. In normal star-forming galaxies, feedback prevents gas from converting too efficiently into stars. The most optimistic models might predict that 30 to 40% of available gas turns into stars over time, with the rest being either ejected from the galaxy or heated to temperatures where it cannot cool and collapse. But achieving several hundred million solar masses of stars by 290 million years after the Big Bang would seem to require either much higher star formation efficiencies or a much larger supply of available gas than theory predicts for that era. Second, the galaxy is physically large, spanning over 1,600 light-years. This might not sound especially large compared to modern galaxies. The Milky Way spans about 100,000 light-years across, but remember that we are seeing JADES GSZ 14-0 when the universe was barely 2% of its current age. For a galaxy to have grown to this size so quickly requires that its dark matter halo was already quite massive by this early time. The growth of dark matter halos through gravitational collapse and mergers is well understood theoretically, and there are limits to how quickly they can grow. Finding large galaxies this early suggests that the initial density fluctuations that seeded these halos must have been more extreme than we observe in the cosmic microwave background, or that dark matter halos grew faster than standard theory predicts. Third, and perhaps most troubling, is the presence of strong oxygen emission lines in the galaxy spectrum. Jake Helton, a graduate student at the University of Arizona, identified these emission lines in observations taken with Webb's Mid-Infrared Instrument, or MIRI. The presence of oxygen so early requires that massive stars had already formed, fused helium and carbon into oxygen in their cores, and then exploded as supernovae, expelling that oxygen into the interstellar medium where it could be incorporated into new generations of stars and ionized by ultraviolet radiation from young hot stars. The entire cycle, from the formation of the first stars to the death of enough massive stars to produce observable oxygen abundance, should take at minimum several tens of millions of years, and more realistically, 100 million years or longer. Yet if we see oxygen at 290 million years after the Big Bang, this implies the first stars must have formed extraordinarily early, perhaps only 100 to 150 million years after the Big Bang, pushing against the theoretical limits for when any stars could form. Some astronomers have suggested that perhaps the first generation of stars was even more massive and short-lived than previously thought, allowing them to synthesize and distribute heavy elements more quickly. Others have speculated about exotic scenarios involving primordial black holes or other unusual physics that might accelerate early chemical enrichment. But none of these explanations are entirely satisfactory, and they often introduce new problems even as they attempt to solve existing ones. The detection of oxygen in JADES GSZ 14-0 was confirmed in March 2025 by two independent teams of astronomers using the Atacama Large Millimeter/Submillimeter Array, or ALMA, a powerful radio telescope in Chile. ALMA detected emission from ionized oxygen atoms at a frequency that, after accounting for the galaxy's redshift, corresponds to a transition in oxygen ions. This detection provided an extraordinarily precise measurement of the galaxy's redshift, accurate to within 0.005%, essentially confirming beyond any doubt both the distance to the galaxy and the reality of its oxygen content. Sander Schouws, a PhD candidate at Leiden Observatory in the Netherlands and first author of one of the ALMA studies, described the finding as like discovering an adolescent where you would only expect bobbies, capturing the essence of the problem. The galaxy has formed and matured far more rapidly than cosmological models predict. JADES GSZ 14-0 is the most extreme and best studied example of this phenomenon, but it is representative of a broader pattern. When astronomers catalog all the bright galaxies Webb has found at high redshift, meaning at great distances corresponding to early cosmic times, and compare the number density of these galaxies with predictions from pre-Webb cosmological simulations, there is a clear discrepancy. The simulations predict that galaxies above a certain brightness threshold should be extremely rare in the first 300 to 400 million years after the Big Bang. You might expect to find one or perhaps a few such galaxies in a survey covering the area of sky that Webb has observed. Instead, Webb finds dozens of them. The exact numbers depend on how you define bright and how you account for various observational biases. But multiple independent analyses agree that there are roughly 5 to 10 times more bright early galaxies than Lambda CDM predicts. This is the crisis that some astronomers have been referring to, a significant statistical discrepancy between theory and observation that cannot easily be dismissed as observational error or bad luck. Rohan Naidu, an astronomer at MIT, was one of the first to identify extremely distant galaxy candidates in early Webb data. He described the experience of finding a galaxy that appeared to date to just 300 million years after the Big Bang as one of the most exciting and unnerving moments of his career. The galaxy, if confirmed at that distance, would challenge fundamental assumptions about how quickly cosmic structure could form. Some of the very early claims about impossibly distant galaxies have since been revised. Initial estimates of distances based only on imaging data, without spectroscopic confirmation, can be unreliable because certain types of nearby galaxies can masquerade as very distant ones. One particularly extreme case, a galaxy initially designated CEERS 93316, that some researchers estimated might be at a redshift of 16.7, was later found through spectroscopic observations to be at a much more modest redshift of around 5, corresponding to a time about 1 billion years after the Big Bang. This is still quite early in cosmic history, but not nearly as problematic for theory as the original estimate would have been. However, even accounting for such corrections and false alarms, the population of confirmed bright early galaxies remains puzzlingly large. Stefano Carniani of the Scuola Normale Superiore in Italy, who led the team that confirmed the distance to JADES GS Z140, emphasized that all observations together tell us that this galaxy and others like it are not like the types of galaxies that theoretical models and computer simulations predicted should exist in the very early universe. The data reveal that something is missing from our understanding, some physical process or mechanism that allows galaxies to form more quickly and efficiently than standard theory suggests. The question is what that missing ingredient might be, and whether finding it requires minor adjustments to astrophysical models or wholesale changes to fundamental cosmology. This brings us to the possible explanations that scientists have proposed to resolve the discrepancy between Webb's observations and theoretical predictions. These explanations fall roughly into 3 categories. First, perhaps the observations themselves are being misinterpreted, and the galaxies are not as massive or as distant as they appear. Second, perhaps the astrophysics of galaxy formation in the early universe is different from what we have assumed, allowing galaxies to form faster or more efficiently without requiring changes to cosmology. Third, perhaps something is fundamentally wrong with our cosmological model, and we need to revise our understanding of the universe's expansion history, dark matter properties, or other basic assumptions. Let us examine each of these possibilities in turn, starting with the possibility of observational misinterpretation. When astronomers observe a distant galaxy with Webb, they do not see it as a resolved collection of individual stars. Instead, they see a small fuzzy blob of light, sometimes just a few pixels across in the detector. From this blob, astronomers must infer the galaxy's properties, including its distance, its mass, and its star formation history. The distance is typically determined from the redshift, which can be measured in 2 ways. Photometric redshift relies on measuring the galaxy's brightness through multiple filters that sample different wavelength ranges. By comparing the pattern of brightnesses across these filters to theoretical models of galaxy spectra, astronomers can estimate the redshift. This method is fast and can be applied to many galaxies simultaneously, but it is not perfectly accurate and can sometimes be fooled by unusual galaxy properties. Spectroscopic redshift, obtained by spreading the galaxy's light into a spectrum and identifying specific emission or absorption features, whose wavelengths are known from laboratory measurements, is much more reliable but requires longer observation times and is therefore used on a smaller sample of carefully selected targets. All of the most extreme early galaxies that have generated the most discussion, including JADES GS Z140, have had their distances confirmed spectroscopically, so we can be confident they are genuinely at the distances claimed. However, inferring the mass of a distant galaxy is more fraught with uncertainty. The simplest approach is to assume that all the light from the galaxy comes from stars, and to use stellar population models to estimate how much stellar mass is needed to produce the observed luminosity. This works reasonably well for normal star-forming galaxies, but it can fail spectacularly if other sources contribute significantly to the light. In particular, actively accreting supermassive black holes, also called active galactic nuclei or AGN, can be extraordinarily luminous, sometimes outshining entire galaxies while contributing negligible mass. In August 2024, a team led by Catherine C.H. Worowski, a graduate student at the University of Texas at Austin, published a study in the Astrophysical journal suggesting that some of the apparently most massive early galaxies might actually be much less massive than initially estimated. The culprit appears to be supermassive black holes. When matter falls onto a supermassive black hole at the center of a galaxy, it forms an accretion disk, a swirling vortex of gas heated to millions of degrees by friction and gravitational compression. This accretion disk radiates enormous amounts of energy across the electromagnetic spectrum, from X-rays to infrared. For distant galaxies observed in the infrared with Webb, the emission from an AGN can make the galaxy appear much brighter and hence apparently more massive than it truly is if you mistakenly attribute all the light to stars. C.H. Worowski and her team carefully analyzed galaxies that Webb had identified as unusually bright and massive in the early universe. They found that many of these galaxies show signs of AGN activity, including rapid variations in brightness, certain characteristic colors, and spectroscopic evidence of fast-moving gas. By accounting for the contribution of AGN to the total light, they estimated that many of these galaxies are actually 2 to 3 times less massive than previous estimates suggested. When these AGN-dominated galaxies, colorfully nicknamed little red dots because of their compact size and red color in Webb images, are removed from the statistical samples, the remaining population of early galaxies is less dramatically in tension with theoretical predictions. Steve Finkelstein, a professor at the University of Texas and co-author of the study, stated explicitly that the bottom line is there is no crisis in terms of the standard model of cosmology. Anytime you have a theory that has stood the test of time for so long, you have to have overwhelming evidence to really throw it out, and that is simply not the case. This represents the optimistic interpretation, the idea that careful analysis and better understanding of the data will resolve the discrepancies without requiring fundamental changes to our cosmological model. However, this interpretation is not universally accepted. For one thing, even after removing the AGN-dominated galaxies, there remain roughly twice as many massive galaxies in the early universe as Lambda CDM predicts. This is a smaller discrepancy than initially appeared, but it is still statistically significant and demands explanation. Moreover, galaxies like JADES GS Z140 do not appear to be dominated by AGN. The spectroscopic analysis indicates that most of the light comes from young stars rather than from an accretion disk around a black hole. The galaxy's large physical size, over 1,600 light-years, is much larger than typical AGN emission regions, which are usually compact, less than a light-year across. So while AGN contamination explains some of the apparently overmassive early galaxies, it does not explain all of them, and it particularly does not explain the most extreme cases like JADES GSZ 14-0. This brings us to the second category of explanations: modifications to the astrophysics of galaxy formation, without changing the underlying cosmology. Perhaps galaxies in the early universe formed stars more efficiently than they do today, converting a higher fraction of available gas into stars before feedback mechanisms could eject the gas or halt star formation. Or perhaps the initial mass function, the distribution of stellar masses produced in a burst of star formation, was different in the early universe. If the first generations of stars were systematically more massive than stars today, they would burn brighter, produce more heavy elements per unit mass, and die more quickly, potentially accelerating the apparent evolution of early galaxies. Another possibility involves the properties of dark matter itself. While we call it cold dark matter because it moves slowly, at least compared to the speed of light, there are theoretical variants where dark matter has slightly different properties. If dark matter particles interact with each other through forces beyond gravity, even very weakly, this could affect how quickly dark matter halos collapse and grow in the early universe. Or perhaps primordial black holes that formed directly from density fluctuations in the very early universe rather than from stellar collapse, played a role in seeding the first galaxies by providing gravitational wells around which matter could collect more efficiently. Each of these ideas has its proponents and its problems. Changing the initial mass function or star formation efficiency to make early galaxies brighter and more massive tends to create conflicts with other observations, such as the rate of supernova explosions or the amount of ionizing radiation in the early universe. Modified dark matter models often struggle to explain the full range of cosmological observations that lambda-CDM handles so successfully. Primordial black holes face their own constraints from various observations and are generally considered speculative. The third category of explanations involves more radical changes to cosmology itself. One possibility that has received serious attention is called early dark energy. In the standard lambda-CDM model, dark energy, the mysterious force causing the universe's expansion to accelerate, has a constant density that does not change over time. But what if dark energy was not constant in the early universe? What if there was a component of dark energy that existed only briefly, perhaps around the time when the cosmic microwave background was emitted, about 380,000 years after the Big Bang, and then quickly decayed away? Such early dark energy would have affected the expansion history of the universe in ways that could potentially allow structure to form slightly earlier than in the standard model. This would not dramatically change the predicted age of the universe or the basic timeline of cosmic history, but it might allow dark matter halos and the galaxies within them to grow somewhat faster, partially explaining the unexpectedly bright early galaxies. The catch is that adding early dark energy to cosmological models tends to worsen other existing tensions, particularly the Hubble tension, a separate and arguably more serious problem where different methods of measuring the universe's current expansion rate give inconsistent answers. If you tune early dark energy to solve the problem of overmassive early galaxies, you tend to make the Hubble tension worse, and vice versa. This suggests that early dark energy, while an interesting idea, is probably not the complete solution. Some researchers have proposed even more radical modifications, such as changes to the theory of gravity itself, modifications that would alter how matter clumps under gravitational attraction in the early universe. These ideas remain on the fringe of mainstream cosmology because they typically struggle to explain the wealth of cosmological observations that lambda-CDM handles so successfully. The cosmic microwave background, the abundances of light elements produced in Big Bang nucleosynthesis, the large-scale distribution of galaxies, the acceleration of cosmic expansion. Lambda CDM explains all of these with remarkable accuracy using only a handful of parameters. Any proposed replacement or modification must do at least as well across this entire range of phenomena, and so far no alternative theory has demonstrated that it can. This brings us to an important question. What do scientists actually think about all of this? Is there genuine consensus that cosmology is in crisis, or is that assessment overblown? The answer, unsurprisingly for a vibrant field of active research, is that opinions vary. Some astronomers, particularly those most involved in analyzing Webb's early galaxy data, believe there is a significant problem that demands new physics to resolve. Others, often theorists and cosmologists who work on the broader structure of cosmological models, tend to be more skeptical that the Lambda CDM framework is in serious trouble. Mike Boylan-Colchin, a cosmologist at the University of Texas who has studied the early galaxy problem in detail, told journalists that most people would put their money on an astrophysical explanation right now, meaning explanations that involve changes to how we understand star formation and galaxy assembly, rather than changes to fundamental cosmology. But he acknowledges that the jury is still out, and that more data will be needed to definitively resolve the question. Carl Gebhardt, a professor of astronomy also at the University of Texas, takes an even more conservative view, suggesting that the field is relatively data-poor despite the excitement around Webb, and that some of the more dramatic claims about cosmology being broken are premature. He points out that when you have only a few data points, it is easy to overinterpret them or to jump to conclusions that may not hold up as more observations accumulate. This is a common pattern in science. A new instrument or technique opens a previously inaccessible window on nature, reveals unexpected phenomena, and initially there is confusion and debate as researchers try to understand what they are seeing. Over time, as more data accumulates and as analysis methods improve, the picture usually becomes clearer. Sometimes the early indications of revolutionary discoveries fade away as systematic errors are identified and corrected. Other times, the revolutionary discovery stands firm and forces the field to adapt. It is too early to say definitively which path the early galaxy problem will take. One reason for cautious optimism that the problem can be resolved without breaking cosmology comes from comparing Webb observations with older data from the Hubble Space Telescope. Nashwin Sapti, an astronomer at Johns Hopkins University, led a study published in 2024 that looked carefully at the expected number of galaxies at various masses in the early universe. Sapti and his colleagues reasoned that if the ultramassive galaxies Webb found required changes to the cosmological model, specifically changes to how matter was distributed in the early universe to seed more massive structures, then Hubble should also have seen evidence of these changes in the form of more abundant smaller galaxies. Hubble, which primarily observes in ultraviolet and visible light rather than infrared, is actually better suited than Webb for detecting certain types of star-forming galaxies because ultraviolet light traces young, hot, massive stars. The team found that the Hubble data do not show the expected overabundance of smaller galaxies that would accompany cosmological changes severe enough to explain Webb's most massive early galaxies. As Sapti put it, Hubble really does not give you much wiggle room to play around with cosmology, suggesting that the source of the ultramassive galaxies is very likely astrophysics rather than cosmology. However, this argument is not airtight. As Boylan-Colchin pointed out, Hubble and Webb do not necessarily observe the same populations of galaxies. Galaxies that are luminous in the infrared, where Webb operates, might be faint or invisible in the ultraviolet where Hubble looks, perhaps because they contain large amounts of dust that absorbs ultraviolet light but allows infrared to pass through. If the most massive early galaxies happen to be dusty, and therefore preferentially detected by Webb but missed by Hubble, then the comparison between the two datasets becomes more complicated. Another important consideration is that the field of early galaxy studies is evolving rapidly as Webb continues to collect more data and as analysis methods improve. The initial estimates of galaxy masses and distances were based largely on imaging data, essentially pictures of the sky taken through various filters. These imaging surveys can cover large areas and detect many galaxies, but they provide limited information about each individual galaxy. Spectroscopic follow-up, where the light from a galaxy is spread into a spectrum showing how brightness varies with wavelength, provides much richer information including precise distance measurements and detailed constraints on the galaxy's stellar population, chemical composition, and the presence or absence of AGN. The JADES program and other similar efforts are now conducting extensive spectroscopic surveys of early galaxies with Webb. As this spectroscopic data accumulates, astronomers will be able to refine their estimates of galaxy masses, better identify which galaxies are dominated by AGN, and generally paint a more accurate picture of the early galaxy population. It is entirely possible that within a few more years, as this data accumulates, and as theoretical models are refined to incorporate new insights, the apparent tension between observation and theory will lessen or even disappear. Science has seen similar situations before. In the early 20th century, observations of galaxy rotation curves seemed to violate Newton's laws of motion until the existence of dark matter was proposed to resolve the discrepancy. In the 1990s, observations of distant supernovae revealed that the universe's expansion is accelerating, a completely unexpected finding that led to the introduction of dark energy into cosmological models. In both cases, the initial surprise gave way to new understanding that preserved the overall framework of physics while adding new components. Perhaps the early galaxy problem will follow a similar trajectory, resolved by better understanding of star formation physics, AGN contributions, or other astrophysical details, without requiring fundamental changes to lambda-CDM cosmology. However, we must also remain open to the possibility that Webb has genuinely discovered something that requires deeper changes to our models. The history of science also includes examples where unexpected observations revealed genuine flaws in prevailing theories and forced major revisions. When Edwin Hubble discovered in the 1920s that the universe is expanding, it overturned the then-standard assumption that the universe was static and eternal. When Vera Rubin and others in the 1970s demonstrated convincingly that galaxies contain far more mass than can be accounted for by visible stars, it forced cosmologists to take seriously the possibility that most of the universe's matter is in an invisible form. If Webb's observations of early galaxies ultimately require modifications to lambda-CDM, it would not be the first time that careful astronomical observations have revolutionized our understanding of the cosmos. The early galaxy problem is particularly interesting because it connects to other areas of tension in cosmology. The most serious of these is the Hubble tension, the disagreement between different methods of measuring the universe's expansion rate. Local measurements using supernovae and other distance indicators give a Hubble constant of about 73 kilometers per second per megaparsec, while measurements derived from the cosmic microwave background give a value of about 67. This roughly 10% discrepancy may not sound large, but it is statistically highly significant given the precision of modern measurements, and it persists despite years of effort to find systematic errors that might explain it. Some proposed solutions to the Hubble tension, such as early dark energy, predict specific signatures in the early universe that might manifest as changes to the abundance or properties of early galaxies. So resolving the early galaxy problem might also shed light on the Hubble tension, and vice versa. Another connection involves the nature of the first stars. The search for population III stars, The hypothetical first generation of stars composed entirely of hydrogen and helium with no heavier elements has been ongoing for decades, but has so far been unsuccessful. If such stars exist, and if they played a significant role in early galaxy formation, they might help explain some of Webb's findings. Population III stars are predicted to be very massive, perhaps 100 to 300 times the mass of the Sun, burning at extraordinarily high temperatures and producing copious amounts of ionizing radiation. They would die quickly as parent stability supernovae, explosions so violent that they completely disrupt the star without leaving a remnant black hole or neutron star. If the first galaxies contained significant populations of these exotic stars, it could help explain both their brightness and their rapid chemical enrichment. However, detecting individual population III stars is extraordinarily challenging because they existed so long ago and were so rare. Even Webb's unprecedented sensitivity may not be sufficient to directly observe them. Instead, astronomers look for indirect signatures, such as specific patterns in galaxy spectra that might indicate the presence or recent presence of population III stars. So far, these searches have been inconclusive, neither definitively confirming nor ruling out the existence of population III stars in the observed early galaxies. The James Webb Space Telescope continues its observations, and each new deep field survey adds to the catalog of early galaxies available for study. One of the most ambitious programs, the first reionization epoch spectroscopic complete survey, or FRESCO, aims to obtain spectra of hundreds of galaxies in the first billion years after the Big Bang. These spectroscopic observations will allow astronomers to measure precise redshifts, determine whether AGN are present, identify chemical abundances, and measure star formation rates with much greater accuracy than is possible from imaging alone. Similarly, the JWST Advanced Deep Extragalactic Survey continues to expand its coverage, observing additional fields and going deeper in exposure time to detect ever fainter and potentially more distant objects. With each passing year, the statistical sample of well-characterized early galaxies grows larger, and the conclusions that can be drawn from the data become more robust. Theoretical work is also advancing rapidly. Cosmologists are running new generations of computer simulations that incorporate more detailed physics of star formation, stellar feedback, black hole growth, and chemical enrichment. These simulations are computationally expensive, often requiring months of runtime on the world's largest supercomputers, but they provide essential tools for interpreting Webb's observations. By varying the assumptions built into the simulations and comparing the results to observed galaxy properties, researchers can test which physical processes are most important for determining how galaxies form and evolve. Recent simulation work has explored scenarios where early star formation is more bursty than in the present day, with brief, intense episodes of star formation separated by longer quiescent periods. Such bursty star formation might allow galaxies to temporarily appear very bright when observed during a starburst phase, potentially explaining why we see more bright galaxies than steady star formation models would predict. Other simulations have investigated the role of supermassive black hole feedback in the early universe. While black holes are typically thought of as growing gradually over cosmic time, some theoretical models suggest that black holes might form directly from collapsing gas clouds in the early universe, bypassing the usual stellar evolution pathway, and these primordial black holes could grow rapidly to supermassive status within the first few 100 million years. If such supermassive black holes are common in early galaxies, their feedback effects might actually help rather than hinder galaxy growth by compressing gas and triggering star formation in ways that standard models do not account for. One fascinating aspect of the early galaxy problem is how it illustrates the interplay between different areas of physics and astronomy. Understanding galaxies at the edge of observable reality requires knowledge not just of cosmology, but also of stellar astrophysics, how stars form and evolve, of nuclear physics, which determines how elements are synthesized in stellar interiors, of atomic physics, which governs how gas cools and emits the light we observe, and of radiative transfer, how light propagates through dusty, clumpy media. No single research group possesses expertise in all these areas, which is why collaborative efforts involving dozens or even hundreds of scientists from multiple institutions and countries have become the norm for major observational programs like JADES. These collaborations bring together observers who operate telescopes and collect data, theorists who develop models and run simulations, and specialists in specific areas like spectroscopy, stellar populations, or AGN physics. The resulting scientific papers often have author lists that run to dozens of names, reflecting the genuinely collaborative nature of modern astrophysics. The question of what Webb has found at the edge of reality also connects to deeper philosophical questions about the nature of scientific knowledge and how we come to understand the universe. Science proceeds not by proving theories correct, but by testing them against observation and discarding or modifying those that fail the tests. A theory that has survived many tests without being falsified earns our confidence, but it can never be proven absolutely true because we can never test it under all possible conditions. Lambda CDM cosmology has passed an enormous number of tests over the past several decades. It correctly predicts the pattern of temperature fluctuations in the cosmic microwave background. It accounts for the abundances of light elements like deuterium, helium, and lithium produced in the first few minutes after the Big Bang. It explains the large-scale clustering of galaxies and the existence of vast cosmic voids and filamentary structures. It predicts the accelerating expansion of the universe revealed by supernova observations. This track record gives us confidence that Lambda CDM captures something fundamental about how the universe works. But confidence is not certainty, and part of what makes science powerful is its willingness to revise even well-established theories when new evidence demands it. The galaxy's Webb has found at cosmic dawn may or may not ultimately require such revision. As of now, the jury remains out. What we can say with confidence is that Webb has opened an extraordinary new window on the early universe, revealing phenomena that challenge our understanding and demand explanation. Whether those explanations will be found within the existing framework of astrophysics and cosmology, or whether they will require more fundamental changes, remains to be determined. Either outcome would be scientifically valuable. If the discrepancies can be resolved through better understanding of galaxy formation physics, it will represent a major advance in our knowledge of how cosmic structure emerges from the smooth, initial conditions of the early universe. If instead the observations require modifications to Lambda CDM, it will be even more exciting, representing a potential breakthrough toward a deeper understanding of cosmology. The process of determining which path we are on is the essence of how science works, through the creative tension between theory and observation, between models and measurements, between our expectations and what nature actually reveals when we look carefully enough. Looking toward the future, several observational programs in the coming years will help clarify the situation. Webb will continue its deep surveys, accumulating larger samples of spectroscopically confirmed early galaxies and pushing to ever greater distances. The telescope's instruments are working beautifully, exceeding their design specifications in many ways, and the mission is expected to continue for another decade or more, perhaps even longer if fuel reserves hold out and no catastrophic failures occur. Ground-based telescopes are also contributing. The Atacama Large Millimeter Array, with its ability to detect emission from molecules and atoms in distant galaxies, is providing complementary data to Webb's infrared observations. New extremely large telescopes are under construction, including the 30-meter telescope and the Extremely Large Telescope, which will have mirror diameters of 30 meters and 39 meters respectively, dwarfing current facilities. When these instruments come online in the next few years, they will be able to obtain spectroscopy of faint galaxies much more quickly than Webb can, allowing for larger statistical samples and better characterization of the early galaxy population. Future space missions are also planned that will complement Webb's capabilities. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will have a field of view more than 100 times larger than Webb while maintaining comparable resolution. Roman will be able to survey large areas of the sky much faster than Webb, potentially discovering thousands of early galaxies and allowing for statistical studies that are impossible with smaller samples. Its wide-field imaging will be particularly valuable for understanding how common the most massive early galaxies are and whether their properties vary across different regions of the sky. The European Space Agency's Euclid mission, launched in 2023, is also beginning to provide data on distant galaxies. While Euclid is primarily designed to map the large-scale distribution of galaxies to constrain dark energy properties, its wide-area surveys will also sample the early universe and provide complementary data to Webb's deep pencil beam observations. By combining data from all these missions and telescopes, astronomers hope to build a comprehensive picture of galaxy formation and evolution from cosmic dawn to the present day. The theoretical community is also gearing up for the next generation of simulations that will attempt to match the full range of Webb's observations. The flagship run, a forthcoming hydrodynamical cosmological simulation, aims to model a large representative volume of the universe with unprecedented resolution and physics fidelity. This simulation will track not just the gravitational dynamics of dark matter, but also the complex baryonic physics of gas cooling, star formation, stellar feedback, black hole growth and feedback, magnetic fields and chemical enrichment. By comparing the simulated universe to the real universe as observed by Webb and other telescopes, researchers hope to identify which physical processes are most important in shaping galaxy evolution, and to test whether current theoretical frameworks can reproduce the full range of observed properties. If the simulations succeed in matching observations, it will provide validation that we understand galaxy formation. If they fail, it will point towards specific areas where new physics is needed. One of the most exciting possibilities is that Webb might detect galaxies at even greater distances than JADES GSZ 14-0, pushing back the observational frontier to even earlier cosmic times. The theoretical limit for how early galaxies could form is somewhere around 100 to 150 million years after the Big Bang, the time required for the first stars to form and begin ionizing and enriching their surroundings. Detecting galaxies from this era would be extraordinarily challenging. They would be extremely faint, their light redshifted to wavelengths at the very edge of Webb's sensitivity range, and they would likely be small and difficult to distinguish from noise in the images. But Webb's near-infrared camera and its spectrographs are capable in principle of detecting such objects if they exist and if they are bright enough. Some observing programs are specifically targeting ultra-deep fields, regions of sky where Webb will stare for dozens or even hundreds of hours, accumulating enough light to potentially reveal the faintest and most distant galaxies. If such observations succeed in pushing into the era of first galaxy formation, they will provide crucial data on the transition from a universe with no stars to a universe with stars, one of the most important but least understood phases in cosmic history. The early galaxy problem also has implications for the study of reionization, the process by which the neutral hydrogen gas filling the universe in the first few 100 million years after the Big Bang was ionized by ultraviolet radiation from the first stars and galaxies. Reionization is believed to have been completed by about 1 billion years after the Big Bang, transforming the universe from a neutral opaque state to an ionized transparent state. The timing, duration, and sources of reionization are major unsolved problems in cosmology. If early galaxies are more numerous and luminous than previously thought, as Webb's observations suggest, then they might have contributed more to reionization than standard models predict. This could potentially resolve some puzzles about reionization, such as whether there were enough ionizing photons available to complete the process by the observed time. Alternatively, if AGN are common in early galaxies and contribute significantly to their ionizing radiation output, that would change calculations of how reionization proceeded. Upcoming observations with Webb and with radio telescopes sensitive to the 21-centimeter line of neutral hydrogen, a direct probe of reionization, should help clarify these questions. It is worth stepping back for a moment to appreciate the sheer scale of the questions we are grappling with. We are asking how the first structures emerged in the universe, how matter went from an almost perfectly smooth distribution just a few 100,000 years after the Big Bang to the rich tapestry of galaxies we see today. We are probing conditions in the universe when it was less than 2% of its current age. Temperatures were thousands of times higher, and the laws of physics were operating in regimes far removed from anything we can replicate in laboratories. We are doing this by collecting photons, individual particles of light that have traveled across billions of light years of expanding space for most of the history of the universe before finally arriving at the mirrors of our telescopes. And from these photons, painstakingly counted and analyzed, we are reconstructing the conditions under which they were emitted, inferring the properties of galaxies that existed when the universe was young, and testing our theoretical models of how cosmic structure forms and evolves. This is an astonishing achievement of human ingenuity and persistence, and the fact that we can do it at all is a testament to the power of science and technology working in concert. The story of JADES GS Z14-0 and the other ultra-distant galaxies Webb has discovered is still being written. We do not yet know how it will end, whether these galaxies will ultimately be explained within the framework of standard cosmology, or whether they will force a rethinking of fundamental assumptions. What we do know is that Webb has delivered on its promise to revolutionize our view of the early universe, that it has raised profound questions that will drive research for years to come, and that the process of answering those questions will deepen our understanding of the cosmos regardless of the specific conclusions we reach. This is how science advances, through cycles of observation, interpretation, debate, and refinement, gradually converging on explanations that better and better account for what we observe. For those of us following along from outside the research community, it is a privilege to witness this process unfold in real time. We are living through a period of extraordinary discovery in astronomy and cosmology, when powerful new instruments are revealing the universe in unprecedented detail and challenging us to think more deeply about fundamental questions. The galaxies at the edge of reality, the objects that should not be there according to our models, are not problems to be solved quickly or easily. They are invitations to look more carefully, think more creatively, and push the boundaries of our understanding. They remind us that the universe is under no obligation to match our expectations, that nature is more subtle and surprising than our theories often anticipate, and that there is always more to learn. This is what makes science exciting. Not the accumulation of facts or the validation of existing models, but the discovery of anomalies and contradictions that force us to question our assumptions and develop better explanations. The most important discoveries in science often begin with someone noticing that something does not quite fit, that observations do not match predictions, that there is a puzzle demanding explanation. If you have stayed with me through this comprehensive exploration of one of the most significant challenges in modern astrophysics, I hope you have gained not only an understanding of what Webb has found and why it matters, but also an appreciation for the process by which scientists grapple with unexpected discoveries. The narrative around Webb's early galaxies has evolved significantly even in the relatively short time since the telescope began operations. Early sensational headlines about cosmology being broken have given way to more nuanced discussions about which aspects of the observations are truly problematic and which can be explained with modest modifications to astrophysical models. This evolution reflects the normal healthy functioning of science, where initial reactions based on limited data are refined as more information becomes available, and as researchers have time to think carefully about alternative explanations. The final answer is not yet known, but the path toward that answer is becoming clearer with each new observation and each new theoretical insight. As we close, I want to emphasize that uncertainty and disagreement are not weaknesses in science but strengths. They indicate that the field is active and healthy, that researchers are engaging seriously with challenging data, and that real progress is being made. A field where everyone agrees about everything is likely a field where little new is being discovered. The debates around Webb's early galaxies, the arguments about whether they require new physics or can be explained conventionally, the back and forth between different research groups with different interpretations, all of this is science working as it should. Eventually, through continued observation and careful analysis, a consensus will emerge. That consensus might favor conventional explanations, or it might require significant modifications to our understanding. But whatever the outcome, we will have learned something important about how the universe works, and that is the ultimate goal of scientific inquiry. Thank you for joining me on this deep dive into one of the most fascinating and important ongoing stories in astrophysics. If you found this exploration valuable and want to see more content that examines the frontiers of cosmic discovery with rigor and depth, please consider liking this video and subscribing to the channel. Your support makes it possible to continue creating these comprehensive examinations of the most profound questions we can ask about the universe. Until next time, keep looking up, keep asking questions, and remember that the universe is far stranger and more wonderful than we can easily imagine. Sleep well and dream of galaxies at the edge of reality, impossibly bright and impossibly distant, challenging everything we thought we knew and inviting us to understand the cosmos more deeply.